A white dwarf represents the ultimate retirement phase for the vast majority of stars in the cosmos, forming when a low to medium mass star reaches the end of its life and undergoes a dramatic structural transformation. During a star's active life, it exists in a state of hydrostatic equilibrium, where the outward thermal pressure from nuclear fusion perfectly balances the inward pull of gravity. When the core runs out of hydrogen fuel, fusion slows down and gravity compresses the core, which heats up enough to ignite helium fusion and expand the star's outer layers into a massive red giant. Eventually, the helium runs out too, leaving behind a core composed of carbon and oxygen that never gets hot enough to fuse carbon. Without an energy source to fight gravity, the outer envelope of the star is gently blown away into space, creating a colorful cloud of gas known as a planetary nebula, while the naked, superheated core left behind becomes the white dwarf. Because it no longer has nuclear fusion heat to keep itself puffed up against gravity, a white dwarf becomes incredibly dense by relying on a bizarre quantum mechanics phenomenon called electron degeneracy pressure. According to the Pauli exclusion principle, two identical electrons cannot occupy the same quantum state at the same time. So when gravity squeezes the white dwarf's atoms close together, the electrons fill up the lowest available energy levels and violently resist being compressed any further. This creates a powerful outward pressure that halts gravitational collapse completely independent of the star's internal temperature, squeezing the mass of our Sun into an object the size of Earth. This quantum safety net has a strict mathematical limit calculated by astrophysicist Subramanian Chandrasekhar, who determined that electron degeneracy pressure can only hold back gravity if the white dwarf's mass stays below exactly 1.44 solar masses. Below this threshold, the white dwarf remains stable indefinitely, but if it steals matter from a neighboring binary companion star and crosses this line, its structure fails, causing the entire star to collapse rapidly and ignite a runaway nuclear fusion reaction that destroys it in a brilliant Type 1a supernova. Because a stable white dwarf has no internal fuel source, it acts like a hot cosmic charcoal brick removed from a fire, starting out at temperatures exceeding 100,000 Kelvin and slowly radiating this residual heat into the freezing vacuum of space over unimaginable spans of time. As it cools, the dense carbon and oxygen ions inside its core begin to lock into a rigid, repeating crystalline structure, meaning the interior of an old white dwarf effectively solidifies into a giant cosmic diamond. Scientists estimate that it will take tens of trillions of years for a white dwarf to completely lose its heat and light to become a cold, invisible sphere of degenerate matter known as a black dwarf, which is why not a single black dwarf exists yet in our 13.8 billion-year-old universe.